Okay, so we are going to continue on reactions of aldehydes and ketones. And I had written a short a summary of the reactions of carbonyl compounds. And the ones we had seen before were hydrogenation with a hydrogen gas and a catalyst, which would give rise to the corresponding alcohol. And that does not change the number of carbons in the molecule. And you can see clearly here we've sort of essentially added H2 across the carbon-oxygen double bond, much as we would add it across the carbon-carbon double bond. We could treat carbonyl compounds with either LaH followed by water, or with sodium borohydride, aqueous, and that'll generate the same compound. We can treat aldehydes and ketones with organometallic reagents, for example, alkyl lithiums, for example, followed by water, and that is going to give rise to the alcohol. But this, unlike the reactions where you use the metal hydride, you'll have an extra carbon in the molecule. We can treat them with cyanide, and that's going to give rise to a cyanohydrin. And we pointed out yesterday, or in the last lecture, that cyanohydrins themselves can undergo subsequent reactions to make beta amino alcohols or alpha hydroxy acids. So these reactions we've seen before from carbonyl compounds. We're going to explore a couple of new reactions today. One is the reaction with alcohols in the presence of dry acid. And what that generates is a class of compound called acetals. We're going to explore the reaction with ammonia and its derivatives. And that's going to generate compounds that have names that depend upon what Z is. We're also going to explore reactions with per acids. This is called the Baeyer-Villiger reaction. And interestingly enough, what that tends to give you is drawing is funny now. What this will give you is an ester. And we will talk about the peculiarities of this reaction in a second. And then the last one is the reaction with hydroxide, in which you get what's called a disproportionation reaction to generate an alcohol and a carboxylate. Although this would be only true for an aldehyde, so you end up with the carboxylate. And so this particular reaction is called, so this one is referred to as acetal formation, and I suppose hydrolysis, because they are equilibria. This is called the Baeyer-Villiger reaction. And this is called the Cannizzaro reaction. And we're going to look at these four in this lecture. Oh, I forgot there was room at the bottom here. Okay, so let's start with acetal formation and hydrolysis. So acetal formation and hydrolysis. It's kind of an interesting story. If you take a carbonyl compound, an aldehyde or a ketone, and you dissolve it in an alcohol, there's no reaction. And you can say, well, the reason nothing happens is because although aldehydes and ketones are pretty good electrophiles, the nucleophilicity of an alcohol doesn't match the electrophilicity to get chemistry. In other words, what that means, and we've made this point on a number of occasions, that all reactions require an activation energy barrier. And although aldehydes and ketones have pretty high reactivities, the nucleophilicity of an alcohol together, when you look at the summed energies of the reactivities, it's not enough to climb the barrier to get chemistry. It doesn't give you enough of an activation energy. So the way then that we can get chemistry between alcohols and carbonyl compounds, because the one will simply dissolve in the other because of hydrogen bonding, is to either make the alcohol more reactive, more energetic, right? So in other words, if this is the energy of the aldehyde, right, and that's the energy of the alcohol, then you want to make the alcohol either more reactive, or maybe you make the carbonyl compound more reactive, and that way their summed energy is enough to catapult them over the energy barrier. Well, alcohols are nucleophiles, and the way I could make this alcohol more nucleophilic is to deprotonate it, right, with some base or the other, OH minus, maybe R minus, it doesn't really matter, some base, and generate RO minus, which is actually a much stronger nucleophile than the alcohol. The problem is, if I use the alkoxide with the carbonyl compound, as we pointed out, the alpha H's of aldehydes and ketones are acidic. And the fastest reaction in organic chemistry is proton transfer. So what I would get is not chemistry at the carbonyl site as I require, but I'm going to shift the chemistry to enolate chemistry. I'm going to generate the enolate ion and the alcohol, which is not what I want, right? I really want the alcohol to be reacting with the carbonyl. So making the alcohol more nucleophilic actually also makes it more basic, and the basic chemistry takes over, right? The acid-base chemistry takes over, and I get chemistry at the wrong site. So it falls to me then that the only way to get the reaction to go is to make the carbonyl compound a better electrophile. And so how do we do that? Well, certainly what makes a carbonyl a good electrophile to begin with is that you have an O that is doubly bound to the carbonyl carbon. A good trick is to protonate the O. And we've done this before, right? When we said alcohols were horrible electrophiles for SN reactions, how do we make the alcohol a better electrophile? And the answer was, we just protonate the alcohol. In which case, we have OH2 plus as my leaving group, and I can get SN chemistry. I'll do exactly the same thing with the aldehyde or ketone. I can just protonate it, and what that will do is generate an O plus, okay? And that makes the carbonyl site a much more attractive site for a nucleophile. So even a nucleophile is weakly aggressive as an alcohol, should be able to carry out the reaction on the carbonyl site. And right, so the carbonyl carbon now is activated, and therefore the alcohol, even which is weakly nucleophilic, should be able to muster an attack on the activated carbonyl. So, in other words, we have a choice of either activating the alcohol, which does not work because it's going to shunt chemistry along an alternate pathway, or we can activate the carbonyl, which in this case we can do by simply protonating the O, and that makes the carbonyl carbon a much better electrophile because we're, even though O draws electrons by induction, making the carbon delta plus, O plus can draw the electrons much more intensely, and therefore the dipole on this carbon is much greater. So if I had, if I had delta plus plus here, and this is going to be delta plus 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 because it's, the O plus is putting more electrons. So that's been my strategy. What I'm going to do is to get chemistry by treating the carbonyl compound with an alcohol in the presence of an acid. Now it turns out that for reasons we'll get to in a second, the acid is either dry HCl, in other words, we're taking hydrogen chloride gas. This is not hydrochloric acid, which is HCl dissolved in water. This is HCl gas. So it comes in a lecture bottle, just like nitrogen gas or whatever. I can use dry HCl, or I can use conc sulfuric acid. And you notice I'm making an attempt to minimize moisture from this reaction. Either the HCl gas, or I'm going to use concentrated sulfuric acid. So I'm minimizing the water content, which will become obvious in a little while. And the products of my reaction are going to be the acetal, and I'm also going to get water. I'm also going to get 2 water molecules. So if I were to write the balance equation for my reaction, it would look like this. The carbonyl compound plus 2 alcohols give rise to the acetal plus 2 waters. I'm sorry, no, plus 1 water. There's only 1 water. Now it turns out this reaction is an equilibrium. And so you can imagine immediately then that by Le Chatelier's principle, if I had a lot of water in the system, then it's a law of mass action, the reaction is going to go backwards, which is not what I want. In the current case, if I'm trying to make the acetal, I want my system to be as dry as possible. And therefore what that does is if I have the acid dry, then I'm not adding water to the system, and that's going to tend to push the reaction forward. But more to the point, in order to get chemistry, the best way of doing it is to remove the water from the system as the water forms. And to do that, we run the reaction in what's called a Dean-Stark apparatus. It's called a Dean-Stark apparatus. Now, I draw very badly, and so what I will do is I'll bring one of the Dean-Stark apparatus to class on Monday, the next lecture, so you guys can see it and see how it operates to siphon off the water as it's generated. So clearly, if I minimize the amount of water that comes with the acid, and I need the acid to protonate the O of the carbonyl compound, if I minimize the amount of water that comes in with the acid, and I use the Dean-Stark apparatus to remove water as it's generated, that's going to push the equilibrium towards the side of making water, and in the process of making the organic compound that you desire. So that's my strategy. I'm going to use an acid to protonate my O of the carbonyl, and therefore to activate it to get chemistry. And I will be using a Dean-Stark apparatus to remove the water, and by mass action, the Chatelier's principle, pull the reaction forward. So how does a reaction go? Well, the mechanism is fairly simple. So here's my carbonyl compound, and carbonyl compounds are basic by virtue of the lone pair of electrons on the O, and we had predicted this as that was not today's lecture, that was the other lecture. We had predicted this by virtue when we were looking at carbonyl compounds and the kinds of reactions they would undergo. That's one of the things we said. We'd anticipate them to be basic. And sure enough, let's say I use HCl. They can act as bases, pull off the proton, and I would generate the corresponding oxonium ion. Okay, and I'm going to lose chloride in the process. Well, alcohols, although they're relatively weak nucleophiles, are sufficiently active now to attack the activated carbonyl. That's why we protonated them. So I'm going to attack the carbonyl, and we know that attack of alcohols on anything positive is an equilibrium. So step 1 is an equilibrium because it's acid-base. Step 2 is an equilibrium because all reactions in which alcohols or water attack something positive are equilibrium. So when I carry this out, what I'll generate is this species. I'll have OH, and I'll have OHR. And the reason this is an equilibrium is because if you look, I have a good leaving group, an alcohol, which is 2 bonds away from a source of electron density. So I know, for example, I can go bang, bang, and go backwards. So this is an equilibrium reaction. Well, I can now have an alcohol function as a base and pull off the pull off the H from the O. So I can pull off this proton, and that will generate this species. And this species with an OH and an OR is already at the aldehyde level. Now, so I can call this species, it's sort of halfway between the carbonyl and the acetal. So this is referred to as a hemi-acetal. In other words, it's halfway along the line. And the term hemi-acetal is preferred over the term half-acetal because, that has connotations. So in the next step, what we're going to do is, of course, we're under acidic conditions, we can protonate the O of the OH, and I'm going to lose chloride, and that will generate the protonated hemiacetal. And of course now I've got a great leaving group, 2 bonds away from a source of electron density, and so this is like falling off a log. I'm going to kick out water. That's the water that was generated. It's the water that is in my equilibrium, right? I kick out water, H2O comes off, and I generate this species. And if you look at this species, it really is almost a mirror image of this one, right? It's an activated carbonyl, whereas instead this had an H on the O plus, this has an R on the O plus. Well, an activated carbonyl is going to be good fodder for the alcohol. And if there's enough alcohol in the system, if you have the two equivalents of the alcohol in the system, it can attack the carbonyl carbon, the pi bond will break, it's the repeat of the first exercise, and we will generate this species. And all that is left now is a molecule of the alcohol. Right, we'll come in, attack this oxonium ion. I'm going to lose ROH2+, which I should have lost, let's see, here as well, ROH2+. And that will generate this species, which is my acetal. So if you look at this reaction, it has a couple of features. One, every single step is in equilibrium. Acid-base, attacked by water or an alcohol, in this case an alcohol, on something positive. Right? That's an equilibrium because I can easily expel the OH group. This is an acid-base reaction, equilibrium. Acid-base reaction, equilibrium. Loss of water, equilibrium. Attacked by an alcohol on something positive, equilibrium. Acid-base reaction, equilibrium. So every single step in this reaction is in equilibrium, which is why it was written in this fashion. So if it's an equilibrium, right, we're doomed to never being able to get a yield of 100%. It'll never be quantitative. But there are strategies that one can enact in order to maximize the yield of the organic product. And we've mentioned two. One is to ensure that the proton source comes in as dry as possible. Dry HCl gas or common sulfuric acid. The other is to use a Dean-Stark apparatus, which literally removes the water from the system as the reaction progresses. That way, by Le Chatelier's principle, we pull the reaction forward. And there's a third stratagem that we use, which is whichever of these two reagents is cheaper, right, and liquid, because not all carbonyls or alcohols are liquid, but whichever of these two species is cheaper and is liquid, that's the one we're going to use as the solvent. So imagine then we had a reaction between, say, benzophenone, which is kind of expensive plus it's solid, and, say, methanol. Well, I'd use methanol as a solvent. Okay? If I had some expensive chiral alcohol or something, and acetone, I would use acetone as a solvent, right? Because it's liquid and it's cheap. So I use one of these reagents as a solvent. And what that does is, by Le Chatelier's principle, if I have an excess of one of the reagents, say the acetone, the reaction is under stress, which will attempt to alleviate by removing the excess. And that means moving the reaction towards the right. So there are three strategies we use to maximize the yield. One is to use a dry acid. Two, we use the Dean-Stark apparatus. And what that does is removes water as it's formed. And the third is we use one of the reagents, either the alcohol or the carbonyl compound, as the solvent. Right? And so both of these take advantage of Le Chatelier's principle. Well, really, I guess in a sense, all three do, because if I minimize the amount of water, I'm also trying to ensure that Le Chatelier's principle operates in to my advantage. Okay, so 2 points to make. Point one. Because this reaction is in equilibrium, it means it's entirely reversible. And we talked about this in the last lecture. One of the ways in which I could make a carbonyl compound is by hydrolysis of acetals. Right? It's by hydrolysis of acetals. We can take this and treat it with aqueous acid. You just have to warm it, and it gives rise to the corresponding carbonyl compound and two alcohols. That is literally the reverse of the top reaction. Right? This compound, if it were to be protonated, right? And I just want you to follow this now. There's a I don't know if you guys are familiar with Sesame Street, but there's a little skit on Sesame Street where this kid gets lost, and you know what? Let's not even use that analogy. Let's just say that if I have A going to B, going to C, going to D. So if I go from A to D through B and C, and I want to go backwards from D to A, there's a principle in chemistry called the principle of microscopic reversibility. And all that means, which is the most obvious, one of the most obvious principles in chemistry, is that if I can go from A to D through B and C, then I can go from D to A through C and B, and I'm just going to go backwards in the same direction. So the first species A will form as B, B will then form C, C will form my product. But going backwards, D will form C, C will form B, and then B will form A. So that principle is very nicely illustrated in this example. So if I were to go backwards, what happens? I'm going to take my acetal and protonate it. So I'm going to make that species. So H3O plus comes in, protonates the acetal, and makes that species. Good. So instead of deprotonating going forward, I'm going to protonate going backwards. What happens next? Well, I have a good leaving group, 2 bonds away from a source of electron density. So this lone pair comes in, kicks out the alcohol, and I make that species. Kicks out the alcohol and makes that species. Now going forward, what would have happened was the alcohol attacks this species to make this. What happens next? Well, water can attack the activated carbonyl, because we're in aqueous acid now, so there's abundance of water. Water attacks the activated carbonyl and generates this species. In the forward reaction, what happened was we lost water. So instead of water coming in, going backwards, water is being lost, and so on and so on and so on. Right? So what would have happened here is I would have deprotonated the OH to make the hemiacetal. Then I would have protonated the OR to make that species. The OH group, the electrons would have come in, kicked out the alcohol to make the conjugate acid of the ketone, and then a base would have come in, pulled off the proton, and given rise to the carbonyl. So I can carry this reaction backwards. And in fact, just for the sake of completeness, I think I'm going to just go ahead and do that. So I'll just do it fairly briskly. So if I were to take this reaction and go backwards, I would protonate the O of the acetal, and that would be in equilibrium, and that's going to give me this species. Then I would lose the alcohol, and of course loss of the alcohol is in equilibrium. That would make the activated carbonyl, which would be scavenged by water, because we're in aqueous acid. Water will attack. That will generate an attack by water or an alcohol on something positive is in equilibrium. That will generate OR and OH2. Right, some base, water, will come in, suck the proton off, and I'm at the hemiacetal. If I have the hemiacetal, that species can now be protonated, and we will generate the conjugate acid. But that now leaves me with an alcohol, a good leaving group, 2 bonds away from a source of electron density. So I'm going to lose that species. I've lost H3O plus here. That's in equilibrium because it's the loss of an alcohol from something positive. That's going to give rise to the conjugated carbonyl compound. A water comes in as the base, sucks off the proton, acid-base reaction. Oops, wrong direction. Acid-base reaction, we lose H3O plus, and we make the corresponding carbonyl compound. So this reaction literally can go forwards, right? Forwards into the acetal, or backwards from the acetal into the corresponding carbonyl compound. And of course, I'm going to lose 2 alcohols in the process. Where did the second one go? Here. I'm going to lose the second alcohol in this process. Okay. All right. The other feature in this reaction, though, is that the alcohols need not be 2 separate molecules. In other words, the OH groups, the 2 OH groups that end up attacking the carbonyl, need not come from 2 separate molecules. So I could use a diol. So, for example, I could take a carbonyl compound and treat it with, well, I guess I could have done that. I could have treated the carbonyl compound with a diol, right, in the presence of dry HCl. And the reaction is exactly the same, it's just that the two OHs are bound to the same molecule. In which case my product is going to look like this. Right? So instead of having an acetal where the two R's are attached to different molecules, all I've done here is attach the R's to each other, right? I've attached the two OH groups to each other. And this is a cyclic, oops, that's not good. So this is just a cyclic acetal. And you know, so this can be drawn in nice fancy ways, of course, right? Whoop, don't do that. This can be drawn in nice fancy ways, which you want to get accustomed to, because sometimes it it can look like that, and it's just exactly the same molecule. Or if, for example, I had I could have cyclohexanone, for example, and I can treat that with maybe 1,3-propanediol, in which case my product is going to look like this. Okay, so 1, 2, 3, 1, 2, 3. And again, this will be done maybe with concentric acid or dry HCl, doesn't matter. One last point that I'll make, and we'll see this later on, is that carbonyl compounds, in addition to reacting with diols, can actually react with dithiols. So instead of reacting with ethylene glycol, for example, it could react with the sulfur analog. There are two noticeable differences. One is that the product is called a thioacetal, and in general, whenever sulfur replaces an O, you just use the word thio to indicate the sulfur. But the reaction is it goes to completion. It's not an equilibrium as the top reactions. It goes to completion and doesn't require an acid. And the reason is quite simple, right? In the reaction with alcohols and carbonyls, alcohols are weak nucleophiles, so you need to activate the carbonyl compound so the alcohol is packs enough oomph to carry out the attack. You have to help the alcohol by making the carbonyl compound more active. You don't have to help the thiol. Sulfur is a great nucleophile. Sulfur doesn't need help. Sulfur can attack the carbonyl compound on its own. The other thing is that HS is actually more acidic than HO, right? H2S is a mild acid, much stronger acid than water. And so what happens in this case is you get the O of sulfur, the O of the oxygen, hydrogen bonds to the H of the thiol. And although you don't transfer the proton, what you do is by forming hydrogen bonding, you're using electron density from the O and donating it, in a sense, to this OH bond. So if the O here was, so if this H is pulling electrons from this oxygen, the oxygen by default is pulling electrons from the carbon. So if this carbon is delta plus, this one is delta plus plus plus. Now, it's not as positive as a protonated, as the carbonyl of a protonated O, right? Because this will be delta plus 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 plus. But this carbonyl is more active than this carbonyl, right? It's not as active as the protonated version, but it's more active than this. So what we say is that this hydrogen bonding provides electrophilic assistance. It provides electrophilic assistance to the attack. So the thiol actually does two things. It's a better nucleophile, so it doesn't really need help. Plus, it's a stronger acid, so it provides electrophilic assistance. There's no proton transfer, but you do make a stronger, a more active carbonyl. It turns out that, as we'll see in a little while, this particular reaction in fact, I might as well do that now then. It turns out that I can take, if I wanted to reduce a carbonyl into an alkane, right, or to methylene, what I would do is I would treat it with the dithiol. And what that does is it gives you the thioacetal. Thioacetals can be treated with rainy nickel, and that will generate the corresponding methylene compound. Rainy nickel is an activated form of nickel that is already impregnated, whose surface is already impregnated with hydrogen gas. So it really is, I don't want to say rainy nickel and hydrogen gas because the hydrogen gas is already impregnated. But what it does is a reduction, right? And it's a reduction that bypasses the alcohol level. I go from something at the aldehyde level all the way down to the alkane level. So I'm bypassing the alcohol level. The reaction is very useful because, for example, if I use rainy nickel that was impregnated with D2, I can make the corresponding di-deuterio, the gem di-deuterio compound. So this is a very useful way of carrying out reductions of carbonyls. We will actually see a couple more of those in a little while. Okay, so this is the acetal formation and hydrolysis. Okay, that's one of the reactions of carbonyls. We had looked at these already. Okay, I wonder if I shouldn't just do the no. Okay, so let's look at this one. So the reactions of carbonyl compounds with ammonia and its derivatives. So let's get another page. So reaction with ammonia and its derivatives. So obviously ammonia has the formula NH2. And some of the derivatives of ammonia, so let's say we're going to call the derivative ZNH2. And we just want to look at what the Z's are. So we're going to write this as, let's see, well, that's a Z. Obviously ZNH2, I guess. Well, in fact, maybe the way I should do this is, yeah, okay. The way I should do, no, that's just fantastic. So the way I should probably do this is say Z, then ZNH2, and then NZ. Right, because I did write the equation, did I not, for you? That they react. Let's just write it again. Yeah, so the carbonyls react with a ZNH2 to form, so C double bond N, right, and then the Z. So basically, the H2O, right, what we've essentially done, let's just go back down, so we have it here. What essentially we've done is we've taken the carbonyl compound, reacted it with ZNH2. We're going to extrude water and generate the product, right? This is called a condensation product, right? Because it's formed because you lose water. It's called a condensation reaction. So Z can be several species. The ones we're interested in are, well, obviously when Z is H, then, let's see, what did I have two? So if Z is H, oh, I'm not sure I need two for this one. I'm not sure what I was thinking here, but so Z can be H, in which case ZNH2 simply has a structure HNH2, and that's called ammonia. And then what you have is something with a structure NH, and that's called an imine. So there are amines when the carbon is sp3 hybridized and singly bound to N, that's an amine. When the carbon is sp2 hybridized and so doubly bound to N, it's called an imine. Z can be R, an alkyl group. in which case I have RNH2, and this is a primary amine, right? Primary amine. The species formed is then this, which is called an N-alkyl imine, right? Because the alkyl group is on the nitrogen, so it's an N-alkyl imine. Z can be OH, so I'm dealing with OH, NH2. This is called hydroxyl amine. The product is called an oxy. I can have Cl, so it's called chloramine, and the product is called an N-chloroimine, much like the N-alkyl imine. These are also called N-hydroxyamines, by the way, and the short word is oxy, but they're also called N-hydroxyamines. And in fact, you can probably tell that, right? N-hydroxyamine, you can mush those words together to get oxy. I will pause here for a minute for chloramine. Chloramine is a very toxic compound. It's a very toxic compound. And in fact, they actually use it in water supplies, right, to kill the bugs, kill the bacteria in the water. But you know, on some, if you look at house cleaning agents, there are warnings not to mix house cleaning agents, and certainly never to use house cleaners in a closed room. And the reason is, if you mix house cleaners, because they come in two, well, most come in two versions. There are those that are ammonia-based, and there are those that are bleach-based, and of course bleach is chlorine. What happens if you mix them is that you react the ammonia with chlorine, and you end up making, initially, this species, and then an ammonia molecule pulls off the proton, and you make chloramine. Chloramine is toxic, and it's volatile. And so what happens is, if you're in a closed room, you're breathing in this toxin, right? And so you'll be dead. So just an FYI. If you have NH2, then your compound is NH2, NH2, and some of you may recognize this as rocket fuel. It's hydrazine. And the species, the condensation product, is called a hydrazone. And I'm going to erase this bit of the chloramine. So I'll have my room. And if I have NH, and then a benzene ring with a nitro group here and here. So my species then, I may have to draw it this way. My species then would be NH2NH. This is called a 2,4. So here's my carbon. Here's my ipsocarbon. This is carbon 1. This is carbon 1, carbon 2, 3, 4. It's a 2,4 dinitro phenyl hydrazine. It's called 2,4-DNP. So 2,4-DNP. The condensation product you generate would look like this. I'm going to run short of room here. Let's see, the better way, I guess, is to do it this way. So NH, and then N, double bond C, whatever your group is. And then here, I'll have a nitro group, NO2, nitro group. This is called a 2,4 dinitro phenyl hydrazone. And I'm gonna put asterisks on well, really on these two compounds, and really these three, but mostly this one. It turns out oximes and hydrozones crystallize beautifully. They make wonderful crystals with very, very sharp melting points when you purify them. I mean, melting points on the melting point ranges on the order of half a degree. In fact, it used to be that if you made a carbonyl compound and you were not sure what the identity was, and this is back in the days when NMR and so on was not readily available. What you would do is you'd make the derivative, either the oxime or the hydrazone, or the 2,4-DNP hydrazone, and you would get its melting point. Then you would go to this huge journal, this huge book, and you'd look for the melting point of the oxime or the hydrazone or whatever. And if it said 92 to 92.5, indicate the compound was propanone, then your compound was propanone. It was so good that if you didn't find a melting point that satisfied your range, it would have meant your compound was nude. I mean, it was that good. It turns out though that of course we don't do that anymore because there's NMR and there's IR, which allow you to do much better qualitative analyses. But we still use the 2,4-DNP hydrazone because it turns out that if you look at this compound, and I'll draw it in the next page. If you look at a 2,4-DNP hydrazone, this compound is wonderfully resonance stabilized. There's resonance all over this molecule. And let's move this over to the other side. Right? There's a lot of resonance going on in the 2,4-DNP hydrazone. And so what this means is, with compounds, and I can use this lone pair to go bang, bang, or to go bang, bang, right? And I can access the nitro group in the 2 position and in the 4 position. So there's lots of resonance involved in this molecule. And when compounds are this conjugated, they absorb light in the visible band of the electromagnetic spectrum. So if this compound absorbs, if your carbonyl is such that this compound absorbs light that is violet, then your compound is going to appear reddish. And that's in fact exactly what happens. What you get with a 2,4-DNP is a yellow to red color or precipitate. So if your compound is in fact a carbonyl compound, then when you treat it with 2,4-DNP, you get a yellow to red color or precipitate. So the yellow to red is indicative of the formation of the hydrazone. The color precipitate is indicative of the mass, the size of the carbonyl. When the carbonyls are small, typically less than 6 carbons, then the product is soluble, and therefore it just got a color because it remains in solution. But when it's got a lot more carbons than 6, like 8, 9, 10, then it's not soluble. It falls out of solution, and you get a precipitate. So if I have a compound that I suspect to be an aldehyde or a ketone, what I could do is treat it with 2,4-DNP. If I get a yellow to red color or precipitate, that's indicative of, or that's confirmatory of it being an aldehyde or a ketone. Okay, the mechanism for the reaction is actually fairly straightforward. And it involves some things we've seen already. The, let's say it's ZNH2, because the Z really is irrelevant to the reaction. The ammonia, or whatever this thing is, will carry out electrophilic assistance to the carbonyl, and then I'll have a ZNH2, use a lone pair of electrons on the end, which is not coming out of my diagram. And the corner is a little bit tricky to draw these things with. So ZNH2, that lone pair attacks, and what we do is we end up, and that's an equilibrium, we end up with OH and NH2 Z, and there's a plus charge here. And it looks as if I lose ZNH minus. And ordinarily, I would raise an eyebrow for losing this because that's a strong base. But what you have to remember is that in ZNH2, there's massive hydrogen bonding in this system, right? There's hydrogen bonding in ZnH2 in the sample. So that if I have, this is not a ZnH2, I'm not going to do a whole bunch, but so for example, if I have my carbonyl hydrogen bonded here, and my nucleophile attacks, and I do this, instead of dumping this negative charge on the N, it's actually shuttled to, so it's going to go like here, and this N, that's hydrogen bonded to another ZnH2, and this is hydrogen bonded to another ZnH2. So this negative charge, so when I do this, it's not as if the minus charge is going to be localized on this N. It's going to be distributed between this N and this N, right? I'm going to draw a funny diagram. It's going to go like this, and this, and this, and so on and so on and so on and so on. So it's going to be distributed through the entire system. So no one N bears the brunt of the negative charge. Right, and so of course what happens next is another ZnH2, and you can probably tell where this story is going. Another ZnH2 comes in, pulls off the proton, and that generates this species. All right, so I get OH, NHZ, and I will lose ZnH3 plus. There, I have some acid protonate this species, and my acid could be one of the ZnH3 pluses, right? I protonate here and generate this species, OH2 plus, right? I get OH2 plus, which gives a great leaving group, 2 bonds away from a source of electron density. So this is like falling off a log. I'm going to lose water. And that'll generate the conjugate acid of my product. And all that has to happen now is one of my ZnH2s, or some base, comes in, pulls off the proton, and we generate our final product. So I'll just point out, when I don't know who the acid is, and there's several contenders, it could be this is an acid, that's an acid, this is an acid, that's an acid. So there are lots of contenders for the acid, right? And I don't care who it is, I don't really care, it's just some proton source. So I could use BH as my acid, or BH plus as my acid, doesn't really matter. When I don't care who my base is, it could be the low impaired electrons on the carbonyl, on the amine, or the ZnH2, or anything, or this species or that species. Or the water, it doesn't matter. It's just a proton sponge. I can just use B lone pair. It sucks off the proton, and I get my product. What you'll notice is that nowhere in the reaction does the Z feature. The reaction is entirely between the N and the 2 H's and the carbonyl, which is why in the simplified version, which is not a mechanism, it was written like this. In the old days when you did lasso chemistry, you wrote a lasso around these 2 pieces and you lost H2O. Now, that's not a mechanism, nor will it be accepted as such, but it gives you a sense of the context of the reaction. The Z is irrelevant to the chemistry, which is why, regardless of what Z is, I always get the same type of products, right? My product is going to be C double bond N Z, and that Z, whatever Z was here, remains in my product. Okay, so the last thing we'll do for this lecture is, remember a second ago, or a couple of minutes ago, we looked at a reaction in which we took the carbonyl compound and we treated it with, let's go this way. We treated it with ethane 1,2-dithiol, followed by Raney nickel, and that generated the corresponding methylene. Great. So that's a reduction. It's a 4-electron reduction of the carbonyl compound. Turns out there are other ways of doing that reaction. One can be done in the presence of amalgamated zinc. In other words, that zinc dissolved in mercury, and conc 8Cl. That's going to also give rise to the corresponding methylene. Now, I could use conc DCl and get 2 Ds, conc TCl and get 2 Ts. This is called the Clemmensen reduction. But there's another one that actually uses, first of all, hydrazine in the presence of base in ethylene glycol. Under reflux. And what that generates is exactly the same product. So there are 3 ways in which I can convert a carbonyl into the corresponding methylene. And they vary with pH. So this reaction clearly occurs under basic conditions. The hydrazine is basic, so is the hydroxide. This occurs at neutral pH, right, or near so, because the dithiol is mildly acidic. And then under strongly acidic conditions, the Clemmensen reduction. This one is called the Wolff-Kishner reduction. It's called a Wolff, and it's not Wolff, it's Wolff-Kishner reduction. We are not responsible for the mechanism of the thioether reduction, except for drawing the mechanism for how the thioether is formed, and that's a pretty straightforward reaction, which pretty much resembles the reaction of the acetals, right? That's the acetal type reaction. But the reduction with radionickel is not relevant. You are not responsible for the mechanism of the Clemmensen reduction either, but you are responsible for the mechanism of the Wolff-Kishner reduction. You would notice the reagent, though, for the Wolff-Kishner is hydrazine, which is one of our Z NH2s. So we're going to go ahead and look at this mechanism, but we're going to stipulate that starting from the carbonyl, in the presence of hydrazine, we're going to generate our hydrazone. Right? So we take this as a stipulation because we looked at the mechanism earlier on. And of course, there are multiple steps in this. Those steps are these steps. Right? Those are these steps. Except instead of writing a Z, I'm going to write NH2. Okay, so let's get to the hydrazone. So we're here. In the presence of hydroxide, right, which is a base, we're running the reaction under hydroxide conditions, we will deprotonate the hydrazone, and that will generate its conjugate base. This reaction goes in part because the N is, electronegative, but also I can draw a resonance form. And in that resonance form, I can show the negative charge being shared by the adjacent carbon. Well, this reaction is occurring in solution in ethylene glycol, which is my solvent. And for now, I'm just going to write HB. The ethylene glycol is going to donate a proton to my conjugate base, and that will generate this species. And this is called a diazo species. The diazo species, however, is also acidic. And it's acidic because, again, I've got H attached to N, and this time the N is sp2 hybridized. So the H comes off, I'm going to lose it as water, and I'm going to make this species. Wait a minute, I had an H on here. This entity is unstable and loses nitrogen. So I'm going to lose nitrogen in a step called a de-diazonation. And the product is going to be a carbanion. My product is going to be a carbanion. The carbanion is going to react with the ethylene glycol, which is my solvent. I'm going to generate the corresponding product, which is the methylene. So that's the mechanism of my Wolff-Kishner reduction. So I stipulate the formation of the hydrazone, and then the base comes in, pulls off the proton, the diazo species, the conjugate base, picks up a proton from the medium, and that generates the diazo entity, which is also acidic. It reacts with the base under prevailing conditions, generates the diazenide. This is a diazenide. right? It's got two nitrogens, a double bond, and it's an anion, a diazonide. The diazonide undergoes a de-diazonation, which spits out nitrogen and generates the corresponding carbanion. The carbanion picks up a proton from the medium and generates the corresponding methylene. We will pause here and pick up in the next lecture.